Start. The index of my presentation is the following. I'm going to start talking about what is PT symmetry really fast, then how we associate quantum mechanics with optics via paraxial approximation. Later I will talk about supersymmetry in quantum mechanics, and here I will give a parenthetical example, and later I'm going to modify the supersymmetry in order to apply this to these photonic systems with 2D landscape of complex refractive index. Finally, I will give my conclusions. So, briefly, what PT symmetry says is that sometimes Hermitian systems could be not enough, and we have some examples. So first, let's say that P is a parity operator. P sends, what is calligraphic P, sends P to negative P, the momentum to negative momentum, and X to negative X. There is another operator T, which is antilinear and has the following effect: P goes to negative P, X goes to X, and the imaginary unit to negative I. And there are some results in this sense saying that if a Hamiltonian H commutes with the PT operator, we say that we have a PT symmetric Hamiltonian, and this is important, its eigenvectors are also eigenvectors of PT, then the eigenvalues of H are real. So we have non-Hermitian Hamiltonians with real spectrum. And one of the examples is this family of Hamiltonians, P squared minus IX raised to some to some power. Epsilon is real. When epsilon is equal to 2, we recover the harmonic oscillator. For epsilon greater than 2, we don't have any problems. All its eigenvalues are real. Between 1 and 2, we could have problems. Some of the eigenvalues are not some of the eigenvectors could not be eigenvectors of the PT operator, so the system could have complex eigenvectors, eigenvalues, sorry. And for epsilon less than 1, we have complex, in general complex eigenvalues. So this was studied in 1998. Going to paraxial optics, there is an approximation telling us that when we have a refraction index like this one, that varies in the 3 coordinates, we have these two Maxwell equations and another couple of Maxwell equations. We can approximate all those Maxwell equations via this process over here. The electric field can be expressed by this multiplication. We have a function in the transverse direction of the z-axis and another function in the z-axis. We make a change of variables to dimensionless variables and so on. So we finish with this equation, say that at order 0 we can approximate the Maxwell equations with only this equation, and basically each component of this vector satisfies a Schrödinger equation. So we have a relationship between quantum mechanics and optics So a team in California exploited this relationship in order to make an experiment of a PT symmetric system, but not in quantum mechanics, but in optics. So what they did is to generate a couple of waveguides, and here I have the refractive index. The red line is the real part of the refractive index, and the green line is the imaginary part of the refraction index. So they solved the system and made the experiment, and they noticed that if you injected light in one of the waveguides, the light was traveling back and forth in these two waveguides. If you inject light in the other side, well, you have a similar behavior. Now, if you have a PT symmetric system with this imaginary part of the refraction index of refraction, we have two behaviors. If you inject light that is also eigenvector of the PT operator, light will behave like this. And if you have light that is not eigenvector of the PT operator, all the light will travel in one waveguide. It will obtain energy, and here this positive section of the imaginary part of the index of refraction is gain of energy, or represents gain of energy. So all the light will travel in that waveguide, obtaining more and more energy until it saturates the system. So this experiment were performed 10 years later and published, well, here in 2010. So what we decided to do is to create systems where the refraction index changes not only in the x direction but also in the propagation direction. And in paraxial approximation, the propagation axis is different from the transversal axis because they obey this equation. In the propagation axis, we have only a partial derivative in c, and in the transverse axis, we have a second derivative. So it's a kind of a different behavior for these coordinates. So what we did is to use the time-dependent supersymmetry in the following way.
So this is a one-dimensional wavegrid, right? So the transversal coordinates is just 1 degree of freedom?
Yes, just 1 degree of freedom. So I was saying, okay, so this is the Schrödinger equation right here, a time-dependent Schrödinger equation. So now time is c. What people does is to intertwine, or to propose this intertwining relationship between the operator S0, which is this Schrödinger equation, with another Schrödinger equation via this operator L that is called intertwining operator. So we have one equation and two unknowns. The only thing that we know is S0. We don't know L and we don't know S1. So there are, could happen that we cannot find L, or it is impossible to find it, or could happen that we can obtain a lot of L's and a lot of S1, and that's the situation that we arrive. We have a lot of L1s, a lot of L's, and a lot of S1s for these systems. So the idea to solve this equation is the following. We propose an operator L right here with this form is a first order differential operator in X. U is a function that has to be found later and will be the most important function. And also we need this function that the peculiarity is that it depends only on Z. U will depend on X and Z. So playing with the equations, well, the first thing to ask is that S1 is a Schrödinger operator. In this way, plugging this information, well, this line in the intertwining relationship, we obtain that the new potential will have this shape, and the function U is a solution of the initial Schrödinger equation. Could be a physical solution or a mathematical solution without boundary conditions. That's the first condition. The second condition arises from the observation of the potential. If we have a zero in this function, we will have a divergent behavior in the new potential, and if we have a zero right here, we also will have a divergent behavior. So second condition is to avoid zeros in U at any X and any Z, and to avoid zeros right here. Next, we need to ask something for this potential, because this potential could be a complex. We can see that here we have an I. Also, this function is a complex function, and L1 could be complex. So this is where we play a little bit in the standard quantum mechanics. We could ask this potential to be real. So let me open a parenthesis here to work in Hermitian system, in a Hermitian system. And the Hermitian system is this one. We have a particle in a box. The green line is my potential. And here we have three eigenfunctions. If we imagine that this potential is time independent, but here I have a time dependent potential, because every picture is the picture of the system at different times. So this is time equal to T0, T1, T2, and T3. We have a box that is expanding. One of the walls is moving with constant velocity. And well, we can obtain the solution of this system. And this system was proposed by Fermi, I don't know, like 70 years ago, trying to explain cosmic particles, cosmic rays. He was saying, hey, maybe we can model the galaxy, the whole galaxy, with a particle in a box system where the walls are moving back and forth, back and forth. And this movement of the walls, that he imagined that they could be magnetic fields in the galaxy, will give energy to the particles, and maybe that explains the energy of the cosmic rays that we receive. So this is a system proposed by Fermi. Later they discovered that this was a wrong system for cosmic rays, but but the solution of these systems are known only, well, I think that only when the wall moves with a constant velocity. We can apply the technique, the SUSY technique, the time-dependent SUSY technique, to obtain this new potential. Here we have in gray the potential. This is a trigonometric post-Taylor potential. And we obtain the whole evolution of the eigenfunctions and the potential. Here again we have a wall moving with a constant velocity. And this is the result of applying the SUSY technique once. We can apply the SUSY technique twice, and we obtain infinite well, but now in the middle we don't have a free particle, we have forces. And we can obtain the evolution of this of the eigenfunctions, well, not eigenfunctions, the evolution of the solutions of the Schrödinger equation. We obtain a family of them. And what? This is the power, or this is what we can do with time-dependent SUSY quantum mechanics. More time, please. So let me close this parenthetical information to go back to the slide that I had before. Here I was telling you that we can play with this last equation to ask something for the potential. And what I want to ask now is to obtain a PT symmetric potential. So playing with this equation and defining what is PT symmetry, because PT symmetry was well defined with one-dimensional potentials. And here now we have X and Z, so we need to define what is P. In our paper we play with two definitions of P. Here I want to give an example of one definition of P. P will be an operator that when you apply this operator on a function, what changes is X to negative X and Z to negative Z. The T operator, what gives you after applying the T operator onto a function, is the complex conjugate. This is the standard T, and this is kind of a new P. So, asking the new potential be PT symmetric, we obtain another condition that is complicated. If we find a function U and L satisfying this condition, and also that U and L are never equal to 0, and also that U is solution of the first Schrödinger equation, then we can apply the technique. So we were playing a lot of time with this equation until we found a way to satisfy this function. I mean, to satisfy this condition. So let me present one example. So we are going to play with the free particle, because in optics the free particle represents light moving in an homogeneous medium. So what I'm going to do is to modify this homogeneous medium using SUSY quantum mechanics. So first of all, we need solutions of the free particle. I'm going to use these, I think they are called Gaussian Hermite solutions. So we can see here that in the first line we basically have a phase. Over here we have a Gaussian and some Hermite functions. This is they are solution of the free particle, and I'm going to take U as this superposition. It's a superposition of the solution J plus I alpha. Alpha is a real parameter, and the solution with the next index right here. I forgot to say that J is an integer number. Why we propose this solution? Well, basically to avoid zeros. We know that the Hermite polynomials have zeros. In particular, they have a 0 when x is equal to 0 for the odd index Hermite polynomials, and for even we have 1, I think. So with this combination we will have one even and one odd Hermite polynomial. Adding this, with this superposition, we are completely sure, and actually we prove that we will never have zeros in both functions. So also this function satisfied all other conditions that I needed. So we can apply the technique.
So J, I suppose that will fit my oscillation theorem or something like that.
Yeah, both of them satisfy the oscillation theorem. So while proposing that U, we can obtain exactly the intertwining operator. It's a first order derivative plus this function, and over here in blue I have a polynomial. It's a complex polynomial, but it's a polynomial in X, so it is easy to obtain the logarithm derivative. Also for the new potential, we can obtain this expression where we have a polynomial over here. It's the same polynomial. So we can say that B1 is a rational extension of the free particle, and we can check that this is a PT symmetric potential. This is a PT symmetric extension or rational extension of the free particle. So let me give you an example. If J is equal to 0, U will be the superposition of the function with index 0 and the function with index 1, which can be written in this way. The rational extension of the free particle is this one, so we have closed expression. Also the intertwining operator is an easy expression, but moreover the solutions for this new system can be written in an easy way. Why? Because we use the properties of the Hermite polynomials. So we can express these new solutions for this new system in this closed form. Here I have some pictures of this solution. The first picture is the real part of my potential. Second picture is the imaginary part of my potential. We can check that it's PT symmetric with respect the axis. With respect the origin. A point over here, for example, one dark point over here, will map to the other side as a bright point over here. So it's symmetric with respect the origin. In this picture, we have the intensities of light traveling in this system. I want to emphasize here that I am working in dimensionless variables right here and right here. If we want to go back to the variables where X is in centimeters, Z will be in meters or in hundreds of meters. So the scale is not the same. So this is my one of the solutions. Here I have another solution with a higher energy, or expectation value of the energy, and over here I have another solution with higher energy. If we have the same kind of solution but now with J equal to 1, so we have a superposition of the solution with index 1 and 2. Here I have my rational PT symmetric extension of the free particle. I can write in closed form again my operators, and again I can write in closed form my solutions, and this happens for any J that I give here. I can write everything in a closed form. And now my system, my PT symmetric system, is this one. Again I have the real part of my potential, it represents two waveguides going to the center and then going apart from each other. Here I have another waveguide going to the center and then going away. I have the imaginary part of my potential, and I have here three solutions for this system. So light is traveling in one waveguide going to the center and then jumps to the next waveguide and continue. And this happens also increasing the expectation value of the energy. It goes from one waveguide and jumps to the next one. And until, well, I have an index here, 5. Until 5, I have some leaks outside these waveguides. So we understood the recipe, so we could play a little bit more, and we generate more examples. Remember, the difficult part is to find a seed solution, U. So playing with this U, we could obtain a system like this one, again real and imaginary part. This system has another symmetry. It has a symmetry with respect the axis, with respect this axis, the z-axis. So it's PT symmetric with respect the origin, and also PT symmetric with respect the z-axis. So it represents a waveguide in the transversal direction that the light is moving, but also we have this irregularity at the center. Light in this situation will focus faster and stay a little bit longer focused than the free particle system. So I think in optics they call this effect self-focusing. So we enhance the self-focusing effect in different, and we have the solutions, all the solutions or many solutions for this system. Over here we have another potential with these two symmetries. Is symmetric with respect the origin and symmetric with respect the axis, and we obtain the solutions. This one was obtained using a second order SUSY, in particular the confluent version of the supersymmetric technique. And well, I want to summarize my work, saying that, well, the goal for this work was to construct PT symmetric system that we can imagine in, that we believe they can be taken to the lab and realize, and they can realize them in optics. Second, another important point here is that we modify the time-dependent Darboux transformation. We obtain solutions, exact solution for every system that we proposed. Our system can be experimentally realizable. And finally, something that I believe is important, we add something to the PT community, something else, saying that we could have systems that are not related to eigenvalue equation, to an eigenvalue equation that could be experimentally tested. So the PT community believes that one important point is to have eigenvectors of the Hamiltonian and eigenvectors of the PT operator. Here we don't have an eigenvalue equation for the Hamiltonian. So something needs to be done in the PT community to include these solutions. Okay, thank you.
Well, like your potential, we only have imaginary time for one question.
Or three.
Usually the term self-focusing is used in the case of nonlinear Schrodinger equation. But I agree, you have a sort of self-focusing in this linear case.
Yeah.
So,
Thank you.
Martin? Oh, one question?
If I don't admit it, as yesterday. I wonder about the analytical structure of the functions of the mechanism. I mean, did you put this? It seems that they have some.
I think like different.
Yeah, the very last one. It seems that in the complex plane, it has some poles. Because x is the variable, yeah? And
X
c
and
is a
Z.
parameter. So that if you make the extension to the complex plane for this solution, you have some poles, yeah? In the complex plane. And of course, you show us some pictures in which you have some intensity. I wonder if this intensity was calculated with the conventional inner product.
The intensities were obtained with the
Square modulus?
with the absolute value
Yeah. Okay.
square.
Yeah.
Why? Well, because we were trying to avoid the problems in.
Yeah, I see. To finish this, I wonder if you have some explanation for the possibility to analyze the poles in the complex plane for this field. Because you are using the inner product for C, but the inner product for C is not necessarily translated to the space in which P is defined. I am clear.
Yes, you're clear.
But we can discuss that. I only put your attention in this question.
Yeah. Yeah. We really focus on this object because this is the object that is important for the optical community.
Not necessarily, because optical community, considering non-Canadian characteristics, is also taking into account the orthonormal basis of the space,
Yeah.
which have some physical properties that can be measured in the lower better than the conventional inner product.
Yeah.
I think I am a member of the optical community.
And you don't use that.
And can you go to the potentials, please?
This one?
No, to the potentials, to the one that you are drawing. Because
Okay.
those potentials don't tell me anything. But for example, this one, it's impossible. Not even the real part, not the imaginary part. The next one,
Yeah.
this one is feasible, but then for me it's just a two-way like copper, right? But then the one that induces half gain, half losses inside one of the waveguides. So basically, I actually have a waveguide that is split in the middle by gain and losses, and then any type of light that I would want to introduce into that waveguide, and experimental light, Gaussian beam, will just be radiated because it's not going to be the idea. So I can follow your point.
Yeah.
But precisely like this one is like you have
Yeah.
this radiation, and you avoid it here because you actually have a nice single mode waveguide where you put on top the gain and the losses and everything. But you start from a single mode waveguide, and in the next one it's like it's beautiful, it's perfect, it seems feasible. But then I don't see if I just try to make it, I'm not going to have this nice curves. I'm going to have a square potential if I do it in the lab. It's going to be far away from that, and then my impinging light is going to be Gaussian modes that are kind of propagate, and that would be something I would like to see as an optician.
Okay.
This is super nice, but then if I actually go to the lab or go to a finite element modeling system, can it support the relative modes, the guided modes, and what I would expect to measure in the lab?
Well, we have to do the experiment. Well, just to add something that I did not show, but I have after the things.
Anyway, this is that it is.
We can talk about this
It's
later.
in progress, yeah.
Yeah. Well, here we can, with the same techniques, we can have a waveguide like this, changing in X and Z. So maybe this one is closer to the experiment.
Yeah, but again, for me as an optician, I see that as a waveguide.
Yep.
And then I immediately see that, okay, if this is a waveguide, and I'm inducing more refractive index in points, I would like to spend more time over there. But then in the laboratory, I will not be able to create that in the waveguide. I will put a pulse, and the pulse will go there, and it will spend a little bit more time there that I will not be able to measure because it's going to be super small. And the phase that I'm going to accumulate through the process is going to be super hard to measure in an interferometer because it's really small. And so this is beautiful. Mathematically it's beautiful. I understand that. But then how it helps me to do things in the lab?
Well, the first plot is the lab plot. That was an experiment performed.
Oh yeah, no, I know this one. No.
Yeah.
But the point is that bring yours
To the lab.
to the lab. It's like this ways, they were amazing because they managed to bring it to the lab. So
Yeah.
bring your nice mathematical ideas with nice graphs into the lab picture.
Okay.
This is why this is done in the imaginary.
In the imaginary lab.
If there's no more questions, we can.
Now more questions.
You want the tree?
You have
But the results are very good.
Yeah, beautiful.
Almost like glass.
I don't know.